Yeah, thanks a lot. Also, thanks so much for the organizers for having me here. It's really very special for me and probably for a lot of you to be back in person and talking and giving talks in front of people and listening in. Yeah, so I would like to talk about our results in the group of Markus Greiner, where I'm a postdoc, and we've been working on many localized systems. And so this is a topic that has been introduced already quite a number of times this week, so a detailed introduction is not necessary here. It really stems from this really old question: what happens if I have a non-interacting system that is localized and now we add interactions to this? And despite of a decade-long research essentially on MBL, there's still a lot of open questions, and we've already heard a lot this week that we don't really understand to what extent MBL exists in the way we thought it would. So I don't want to dive too much into this discussion, so when I say MBL, what I usually mean is what we used to call MBL. A system that, at least on our experimental time scales, remains localized, yet has some logarithmic growth of the entanglement. MBL, the reason why I believe MBL has been so widespread and has attracted so much attention over the different communities is that it actually covers a range of phenomena that are, of course, somehow connected, but they're coming from very different fields. So one decisive aspect, of course, is that we have a localization in the system, although we have interactions present in the system. This also leads to the fact that we actually have a very good insulator, although we are living at very high energies. Then associated with that is also that the initial state remains intact for very long times. So we have more of a quantum informational perspective. And then we have a very fundamental perspective that the system actually leads to a breakdown of thermalization and therefore touches aspects of statistical physics. And then we have this growing non-local entanglement, which is a very peculiar phenomenon that was very new for a lot of us. And yeah, these come from very different areas, and I think it's very exciting to have a system that ties together so many different fields. So as experimentalists, the question remains, how can we probe such systems? How can we realize that, and how can we maybe touch some of these questions that I just mentioned? And I see three key challenges in the experiment to actually realize such systems. Isolation. We need a very well isolated system in order to see these entanglement properties and also the localization of the system, that it remains intact. We need to be able to simulate this Hamiltonian in a way that it remains coherent. So we have to manipulate the system and create entanglement in it in a very coherent way. And then finally, to read out these properties, we need very complex observables. That also requires a very good readout techniques. We are working with cold atoms, and that helps us to address these three challenges. So we've first trapped these atoms in vacuum, and that leads to a very well isolated system. We then manipulate them with laser light and let them collide through their inherent collision interactions. And then finally, we take pictures under a high-resolution microscope and therefore can probe this state locally, and from that extract a lot of complex observables. This is how the system looks in our case. So you see here a line that separates vacuum down here from air, and these two lenses together form a high-resolution objective, and the atoms are just trapped right underneath this lower lens. And then we project an optical lattice through this objective in which the atoms can now move around and in which they are trapped. We use bosonic rubidium atoms here. And as a next step, we can also use this system now, this system not only to project the lattice, but also to read it out with the resolution of a single lattice site. And the pictures that we obtain from that, they look like so. So we have a huge cloud of a lot of atoms, and if you zoom in, you can actually find the underlying lattice pattern. So there's a clear lattice structure, and from these pictures, we can, with a very high fidelity, tell if a certain lattice site was occupied or it wasn't. On top of that, we can also now create potentials. So not only lattices, but actually arbitrary potentials, and that really allows us to create site-resolved offset potentials, so little chemical potential offsets that we can set on each lattice site at will. So it gives us a very high control over the system in terms of preparation, and in terms of evolution, and in terms of readout. The actual protocol that we are using for essentially all the experiments that I'm going to talk about looks like so. So we start with a mod insulator of one atom on each lattice site. And for us, it's a very good state because it means that we have a completely unentangled state in the spatial degrees of freedom. So when afterwards, when we cut out our initial state and we define our system, we know that we always start with the very same exact identical initial state. So in this case, that's a state of n lattice sites in a one-dimensional system with exactly one atom on each lattice site. And we can now use the state and evolve it under a well-defined Hamiltonian. And since we do this abruptly, this performs a quantum quench, so the particles now evolve in far from equilibrium. And after a certain evolution time, we take a snapshot of the state, and that just projects the state in Fock space. So this could be such a snapshot. Now, there's one caveat, which is that the fluorescence imaging is actually parity projective, which means we don't resolve all the n atoms that we started with, but fewer ones. So we play a little trick to overcome that. We first expand the atoms along the orthogonal direction before we actually would take the snapshot, and afterwards we image them. And that means we can count the atoms in each column, and from that we can deduce how many atoms have been on that state. So the projection is now a full counting statistics instead of a parity projection. So this would be one of these snapshots that we now deduce. So these are the kind of strings that we work with, and from these we can now construct any kind of complex observables. The fidelities that are involved in this are very high, so we have almost a unity state preparation fidelity per site. Also here the same for the, excuse me, this means readout, almost unity readout fidelity. Also, we can post-select the atom number because we start with a certain atom number and we are never going to have more, so we may have some atom loss, but we can post-select on the initial atom number, on n atoms in this case, and therefore after this, we effectively have no atom loss. And we can also use these slide potentials, which are very, very coherent, so we are far away from any kind of atomic resonances, which gives us really no projective measurements. So there's the photon scattering rate is so low that over the entire evolution time, which can be hundreds of tunneling times, we have maximally one event of one side that gets projected by some photon scattering event. So it's a very coherent system in that sense. The model that we are using here is based on the Bose-Hubbard model, and then we add, in this case, a quasi-periodic potential. So we have the tunneling, we have the interactions, and we add a quasi-periodic potential. We could also add any other kind of disorder statistics. In this case, we chose a quasi-periodic one. So I'm going to call this disorder, but it's a quasi-periodic disorder or potential. The interaction strength for the experiments here, we've chosen it to be about J, but this is in principle tunable. And what we are going to tune mainly is the evolution time and the disorder strength. So these are going to be the main quantities that we are playing with. Now let's start. I want to give you flavors for three different aspects of many-body localization that we probed in our experiment. The first one involves the actual kind of probing the bare state of many-body localization. Can we see the localization? Can we see the breakdown of thermalization and those entanglement dynamics? Then afterwards, I'm going to talk about the critical behavior. What happens if we reduce the disorder such that the atoms start to delocalize? What happens then with these transport properties? It's a very complex question also from a computational point of view. And finally, and that's probably the most timely if I recall the last days, how robust is MBL actually against any kind of thermal inclusion? Do particles in real systems actually remain localized, or is it inherently unstable? Yeah, so let's start with the first topic, the many-body localized state itself. So this would be our system here, in this case 8 atoms on 8 sites. As I mentioned, it's a globally pure state, and it's also a locally pure state because we actually also even locally there's no entanglement in the system yet. Now as we evolve the system, we have some unitary dynamics which will create entanglement in the system, which means if we now locally look at the system, we are going to find the thermal distribution. Because the system is a non-equilibrium system and evolves towards, according to quantum thermalization into such a state. So if now we probe the system, so we take a lot of snapshots of these kind of states, and then we always look at one individual lattice site and now look at the entropy of this individual lattice site. So we compute now first we can compute a histogram of the population of this lattice site, and you can really find that it approaches very much the one of a thermal distribution. So this is now without disorder, and these little points are the data points, and the bars are the prediction from exact numerics, and we can really say that we understand our system very well here. After long evolution times, the system approaches a thermal distribution locally. Now, yeah, we can quantify this with the entropy, the single site entropy, and what we find is that over long evolution times here, we're covering up to hundreds of tunneling times. The system approaches a value in the single site entropy and then remains constant indefinitely. So we really see that the system remains at its steady state once it reaches thermal equilibrium. Now we can do the very same thing again with disorder. Now particles don't spread that much anymore, so we expect particles to retain their initial conditions. So we can't assign any kind of temperature to this anymore. And what we find is that now the histogram looks very different. We have a strong peak around having one particle on the lattice side. So the initial state remains intact. And quantifying this again by the single site entropy, here so as a function of the disorder strength, always after 100 tunneling times, so much larger than any kind of system size, much larger than our longest evolution times, and we find that for small disorders here, we coincide with the prediction from the thermalization, and as we approach about 4 to 5 disorder strength in terms of tunneling, we depart from this. So the system does not thermalize anymore. Instead, we find this departure from thermalization, which indicates the onset of many-body localization in the system. Now, what is the very exciting aspect about this is that this localization, despite this localization, there's still some dynamics going on in the system. And this was found, for example, here in the paper by Jens Barderson, very topical, where they studied the spin chain and they looked at the entanglement entropy over time, the half-chain entanglement entropy over time. And without interactions, there's no dynamics, but in the presence of interaction, actually, there's a slow logarithmic growth. And we were asking ourselves, what does that mean for a system like ours, which is first, it's itinerant, so particles are actually moving, and also we're looking at this not so much in this kind of picture, but more in a number occupational picture. So what does that mean from a microscopic point of view, this kind of logarithmic growth? And it turns out that you can actually separate these dynamics into two different parts. And the first one is what we call the number entropy, where particles move around, and therefore there's going to be some kind of entanglement entropy between two halves of the system. So when particles would cross the boundary, which I set here in the middle, then this would be a very easy depiction, very simple depiction of an entangled state. We're in a superposition of having all particles on the initial side and one particle crossing the boundary. So there's certainly, in this case, an entanglement here. And all these particles crossing the boundary are going to create some kind of entanglement. And it turns out that's exactly this initial rise here, where particles find their localized orbitals, and then we find this constant evolution here. So this is exactly this number entanglement. Now, on top of that, there is a second kind of entanglement, which we call the configuration entanglement. And this involves now particles not crossing this boundary, but really only moving within their systems. So what we find there is that the motion of particles are correlated. In other words, the way particles would arrange in one subsystem correlates with the way they would arrange in the other subsystem. So there's also entanglement involved here, because there's correlations between different particle configurations, but it does not involve particle exchange between these two different subsystems. And it turns out this configuration entanglement is actually exactly this remaining entanglement that we find over here. So this is exactly the part of entanglement that causes this logarithmic growth. So if we can find these kind of correlations of the configurations of particles, we can tease out the entanglement in the system. So you can also mathematically actually strictly separate these two types of entanglements in the sum of these two. Yeah.
So to keep track of entanglement, in principle, you should also look at n-particle correlations, right? Not just right. Yeah. And this already captures this. So
since this captures all kinds of correlations of all kinds of configurations of the particles, it can also be. It's essentially an endpoint correlator. It's a correlator of all different lattice sites together. So there can of course be correlations that don't really affect all those lattice sites, which, for example, here essentially you have two correlated doublons, but it could also be something more complicated. Yeah. Also, since we are always measuring the same basis, this cannot capture all the kinds of entanglement that are in the system. But we can just hope that, although we are just measuring on one basis, we can still capture the essence of what's going on here. And I think the fact that we have a disordered system also helps us to kind of scramble a little bit the axis along with which we have the entanglement present here.
Thanks.
Yeah. Another question?
How many shots do you have to take to actually get good enough statistics such that you capture basically all the moments or the information on all the moments, even in just say the number basis?
Yeah. I mean, in principle, measuring entanglement entropy, of course, scale is very unfavorable. In this case, it's not that bad because actually you only need to measure the probabilities for the different Fock states that are actually occupied, right? So if there's a lot of the ones that are empty, you also never measure them, and so it's kind of assumed that they're zero. So it's actually more favorable than one would think. In particular, if you go to rather localized particles, where the worst thing that happens is like maybe some double on whole pair, but nothing more complex. That being said, still you need a lot of shots. So even for small system sizes like 8 sites, you need up to 1,000 to get a decent error bar, and then you want to average over a lot of different disorders, so that easily goes into many thousand shots. Yeah, even for system sizes like 8 sites. Yeah. So now we set on to measure these two different kinds of entanglement in the system. So first the number entropy, and we can quantify this again by the classical formula Pn log Pn. So now we're counting atoms in the left subsystem and measuring the associated entropy. And here again we find this initial rise, and then afterwards there's the steady state here. So between 10 tunneling times and 100 tunneling times, there's essentially no evolution anymore. So rather fast, the atoms find their spot, and then there's not much tunneling dynamics going on anymore. Now, in the other quantity, there's still a lot of dynamics expected because it's supposed to capture this logarithmic growth of the entanglement entropy. And indeed, if we quantify that here, we do this. So we do this like so. So we take these snapshots A and B, and then we define a correlator which acts on the probability that to find these two different configurations A and B together minus their individual probabilities. So we're looking at whether there are any configurations between these two different configurations present or none. And if we sum over all different kinds of configurations that are possible in these two subsystems, this actually is a probe for the entanglement. It's directly proportional to the configurational entropy in the system. And now when we measure this over time, here again the same range here on the log scale up to 100 tunneling times, we find indeed this logarithmic growth over time. So we can actually add this plot with the previous one and find the very same behavior as before, shown in the paper from Jens Barterson and co-workers. That's all I wanted to say about the many-body localized system. Now let's reduce the disorder a little bit and go to the critical regime, where things are becoming much more complex. And it's conceptually not so clear what is actually the right thing to look at here. So what we did was we tried to capture the transport dynamics in the system based on the correlation functions that we can see in the system. So the 2-point correlations give us directly how far particles move. So when a particle moves from one side to another one, that creates a double on hole pair, and therefore we can see by that how far do particles typically travel in the system. So we define a transport distance, which is really just the average distance that these particles would move, and look at how this changes over time. So without disorder, we have this very fast rise up to where particles delocalize over the system size and then remain there indefinitely. So we indeed delocalize the particles across the entire system, and then afterwards there's no.
Sorry, can you clarify how that's defined? Because I just know where the particles started and where they ended up, right? But I don't know which particle moved where because they're indistinguishable.
You don't know which particles? Yes, they're indistinguishable.
But does that matter? Because it sounds like you're adding up the distance they moved. How do you disambiguate which particle moved where?
What we do is we take the first moment of these 2-point correlations.
Okay,
so it's related to that, but it's true. There's a slide. Yeah. So we just use this here as a quantifier for typical distances that particles would travel. And without disorder, that indeed grows very quickly and particles delocalize. Now, if we look at this now on the in the site resolved manner, we find that indeed there's similar correlations between all kinds of sites in the system. So no matter how far away, particles are correlated equally strongly. So that's again a sign of delocalization in the system. Now we switch on very strong disorder. We are now in the many-body localized regime, and we find that after a few tunneling times, there's not much change anymore going on here. And if we look again after very long tunneling times, after 100 tunneling times here, there's strong correlations between the nearest neighbors, but all the other sides remain uncorrelated. So we find particles tend to hop one side apart, but that's it. There's no further dynamics. So very strongly localized particles here. And if we go in the intermediate regime, we find a behavior where we very, very slowly increase the distance that particles travel, but eventually we hit the system size pretty much as long as we measure. So that tells us that we are only limited by the system size at the very end of our measurements. And most of the time we're actually not limited by the system size. And here what we find is that the particles have such a complex pattern here. So particles tend to hop one side apart, or 4, or maybe 6, or 7, or even 9, but there are other sides that are completely decoupled. So there's kind of a network of sites between particles travel and others not. So those, of course, determined by the interplay of disorder and interaction in the system, but it's not so trivial to figure out how exactly this plays together. However, it matches very well with our exact diagonalization numerics. So all these lines that I show are exactly that. Yeah?
So I just want to make sure I understand this. Is this averaged over all distances, or this from like one particular site?
This is averaged over all distances, yeah.
I'm sorry, overall all sites.
So over all sites with the respective distances, exactly, yeah.
Okay.
Yeah. So we can extract the slopes of these kinds of graphs here, and from that deduce the subdiffusion exponent in this system. And we find indeed that as we increase the disorder strength, that goes further and further down, and that very strong disorder is expected to reach 0. So the transport slows down over the critical regime and becomes slower and slower because subdiffusion sets in and becomes more and more strong. Now the question is, how complex is this network? Like, is this a 2-point correlation function, or is it actually a higher order process? And in order to test that, we looked at higher order correlation functions to see the order of the processes at which the network actually enables the transport in the system. So here, what you find here is the connected correlation functions for different orders. So we start here in the strongly disordered regime. As a function, here's the correlation order. So these are 2-point correlations, 3, 4, and so on. And so you can see there's some 2-point correlation functions. This bar here. So again, the little points are the data points, and the bars are theory. So there's some 2-point correlations, but all the higher orders are strongly suppressed. So these 2-point correlations, they come mainly from these nearest neighbors, right? Now in the thermal regime, there's also some 2-point correlations, which is really this completely localized system. So all sites are coupled equally. But afterwards, the correlations they decay very quickly. So the higher order correlations are also not very strong. And the system is very, very different if we look at the intermediate regime. So you can find here, no matter at which order we look at the system, we find strong correlations. So 3rd, 4th, 5th, and so on, we find strong correlations no matter at what kind of process we look like. And that shows us really how complex the many-body state is in this intermediate regime, because this network is actually a many-body network that drives the delocalization in the system. Now, as a third topic, I want to talk about the avalanche dynamics in the system that we probed by connecting a many-body localized system to a clean system without disorder. So in general, the question is, how stable is actually many-body localization? How robust is it when I would have some local inclusion that is ergodic? And that's a question that is in particular important for a randomly disordered system, because we always expect some rare Griffith regions in these systems. Now we are working here with quasi-periodic potential, which means that we actually suppress those kind of regions, but we can artificially engineer such a system by adding disorder on part of the system and no disorder on the remainder of the system. And now in general, there could be different scenarios of what could happen. For example, there could be, the bath could be so small that the entropy of this bath kind of tries to delocalize the many-body localized system, but it can't because there's not enough density of states of this bath. So the system can't really penetrate, the bath can't really penetrate deep enough in the system, so it kind of gets stuck and the system remains localized. But it could also be that that the entropy from this thermal bath penetrates the many-body localized system further and further and delocalizes one side after the other. And it's under different conditions, one or the other may be the dominating factor here. And we really try to engineer a system where we can observe these kind of dynamics. And the way we do this, I mentioned this, we very similar to before. We have now, again, this one-dimensional system, and part of it has the disorder, part of it does not. And we built, again, this box around it, and this is our one-dimensional system here. So it's very similar to before, except that we only project the disorder on part of the system. And what we see is, these are our results here. So we start now from a state that is completely uncorrelated. So what you find here is the 2-point correlations between all different sites. So here it is among the clean system, among the disordered system, and these are the correlations between disordered and clean system. And we are now at 0 tunneling time, so there's no correlations whatsoever because every site has exactly one particle, so it's our initial state. But now let's see what happens when we evolve the system. And we find that within the bath, all sites become equally correlated. So really particles spread very rapidly throughout the bath. We are here only at 3 tunneling times. Particles spread entirely through this bath. However, in the many-body localized region, particles only spread to the nearest neighbor. So we are strongly localized here. So we really have separate dynamics here between the bath and the many-body localized system, and not much crosstalk between the two. Now, if we go now to very long evolution times, up to 100, we find that this remains the same in the bath and the many-body localized system. Things remain the same, but we find these kind of penetration here into the many-body localized system, from the bath into the many-body localized system. So there are these sites here that also become now correlated. And we can now make this a little bit more visible by averaging over essentially over this. So we now average these different rows. So what you find is the combined correlations, 2-point correlations between bath and MBL with each different site. So here initially there's nothing, and then here there's correlations within the bath and maybe a little bit into the many-body localized system, but not much yet. And here we find this almost exponential decay. And we now quantify this here again by the average distance particles would travel into the many-body localized system. So this is again the first moment of these 2-point correlations, which we call now the penetration depths. And if we now track this over time, we find not that it saturates, that it stops, but actually an increase of this. So the longer we wait, the faster we penetrate into the many-body localized system. And so we can also test this with a small bath and see what happens there. And we find that the behavior is very different. So it actually becomes slower and slower and the system kind of remains. So this would show us that the entropy or the particles kind of get stuck here, whereas here they penetrate farther and farther the longer we wait. So the understanding or our interpretation of this is as follows. So we start with a bath that has a certain density of states. So and now the thermal region, so this bath now can penetrate into the many-body localized system. So the thermal region now grows a little bit because it starts to delocalize the first site. Now afterwards this increases the density of states of this new bath, and therefore it can penetrate farther into the bath, and therefore as a next step when it can penetrate farther, it actually leads to a faster delocalization.
Do you have the same plot in linear scale in time, or I'm just curious how crucial is acceleration?
I think
you have logs.
I didn't plot it here, but I mean linear it would be much slower, of course. Yeah.
I understand. So, but basically, even this accelerating curve will look like it slows down a bit, right? On
a linear scale, I believe so. Yeah. But it is. I mean, the point is that it's going like faster than an exponentially slow process, right? And we can also test this now for different sizes of this bath, and you can indeed find that without any, then we end up with the normal localization length. And as we add more and more bath sites, it really shoots up for 6 or 4. It's like a little bit, but the larger the bath, the farther particles travel into the system. We can also look at now the thermalization site by site. So we are now looking at different sites here, If we look rather close to so this would be one of the first, this would actually be the second site next to the bath, we find that for the 6-site bath, there's some delocalization happening here, but the onset of that is at a later point if we go farther and farther away. So that we can really see that the different localization, the different MBL sites, the different sites in the disordered regime become localized after different times. So there's kind of a delay for the particles to see the bath and to couple to the bath and to become delocalized. It is also just a 2D visualization of this. So you have time here, the sites. So over time, at later and later points, they actually start to delocalize.
So in these experiments, you're looking at fairly, few site correlation functions, right? So is there anything restricting you to small system sizes? Could you go to like a line of 40 or 50 spins? Because in principle, the microscope is capable of that.
Yeah, that brings me perfectly to my conclusion. So we want to get bigger. We also have already looked at 24 sites. And that's indeed something that's very much within our capabilities. We started with a smaller system to understand it very well, but 24 sites are perfectly possible. And 24 sites, bosonic systems already have a really large Hilbert space where at least we can't do numerics anymore. We use this in this case here to measure the Luttinger parameter from the entanglement dynamics of the quasi-particle excitations, but we can also project now disorder on the system. For example, now one could look at much larger MBL sites and attach some bath to it, some small bath. Going even larger, it starts to be challenging. We would have to adapt a little bit the way we project our potentials, but there's no fundamental reason why this shouldn't work. Yeah. And the second project that we are working on right now is just a little outlook, is on topology actually. So we are looking at preferring ground states with interacting bosons in the magnetic field, so Laughlin states in this case. So if someone wants to talk about that, I'm very happy to discuss with you. Yeah, that brings me to the end. Thank you very much for your attention, and I would like to. sorry, just one thing. I want to thank this fantastic team that I can work with. So I have 3 grad students in my team with which I work, and it's just a very big pleasure to work with them. So there's Sushin and Choice and Perrin, and it's really nice. And of course, there's Marcos, our supervisor. So now, thank you very much.
Thanks for the very clear talk. Time for questions. Oh, Taru, go ahead.
Yeah, thank you for a very nice talk. I had a question about your configurational, this entropy you define in terms of probabilities, this probability of A tensor B minus product of probabilities. And you mentioned that is proportional to the actual entanglement, which is related to this, but that sounds very, I don't know, that sounds very hard to, I mean, I can imagine this being non-zero, this configurational entropy you actually measured being non-zero. Even for a classical system, there can be classical correlation which can make it non-zero. So how can it be in general proportional to actual entanglement, which we know is much harder to measure, otherwise we will do it all the time.
Yeah, that's a good point. So the fact that this would be proportional to entanglement is, well, there's actually 2 aspects to the question. One is we indeed rely on the fact that the global state would be pure. Now we have several ways to prove it's pure. One very direct way how we prove that is by adding a copy of this very same state, interfering them and measuring the purity directly, which we did before and which we can do and which we also did for the system. So this is one way how we can prove that the system still remains globally pure. Now, in addition to that, there's a second aspect to what you said, which is why even in a pure system is it actually proportional to the configuration entropy? And that's also not obvious because we are measuring in one basis, right? And in our case, we don't have a rigorous proof that it has to be proportional. We verified this extensively numerically throughout all the parameters that we could think of, but it remains a phenomenological relation essentially.
But can't I just prove it can't be true in general? Because I can construct classical systems which have classical correlations, I mean probabilities, classical probabilities which are not separable will have this always non-zero, while, so isn't that a counter example? I mean, one can easily construct such things.
Yeah, in classical systems, one definitely can find counterexamples. So again, we are kind of relying here on the fact that we are globally pure, which we independently can prove.
I mean, by classical, I mean even quantum Hamiltonians, where I make like some some kind of product states which have some classical correlations.
Oh, I understand. Yeah, I mean, you could also think of actually entanglement that acts in different degrees of freedom, orthogonal to the basis in which we are measuring, right? I don't know if that's what you have in mind, but there's certainly states that don't have that feature. So it's more like a phenomenological approach where we're looking at the particular system, a disordered system, where and MBL, and looked at the relation between these correlations. And I mean, we were kind of trying to find a relation between the actual entanglement entropy, which is just very difficult to measure, and an experimental observable to capture that. And this is the kind of correlations that we found to be very suitable for the system.
I know, yeah, it's very interesting. I had one more question. Maybe I will wait till the end because there may be other questions. I don't want to take up time.
Oh, you're fine. Go ahead.
Other question I had. Okay, thank you. So since you're working with bosons, which are very hard to simulate, right, because they have infinite Hilbert space. Yeah. So even in the ergodic regime, are there correlations which are somehow can never be captured by your numerics? Are there interesting correlations which, I don't know, which are related to hardness of bosonic excited states? For example, we know permanents are hard to calculate numerically and so on. Are there such things are there features in your ergodic side which are somehow essentially about bosons which will not show up in spin systems, but essentially for example, there are interesting things about bosons with light cones. Sometimes you can have slight violation of Lieb-Robinson-like things, which because of infinite Hilbert space per site I was just wondering, how important is it that it's a bosonic system and not a spin system in terms of?
I'm not sure if I grasp all the aspects of the question, but so maybe one thing is so the numerics is exact, so we use exact organization or Kudov propagation to actually have the exact state that we so it's the numerics are exact. So we don't cap the Hilbert space of each site. We cap it only at the global particle number, right, which is conserved. So the numerics actually capture the system exactly. Was that your question, or was there something else to it?
Yeah, I guess that, you already, sometimes you're saying the number of bosons is so few in your system that you can go to the maximum number of Hilbert space, I see.
Yeah, so we have one boson per site, and the largest system that we were looking at here were 12 bosons.
Right, that's very small.
And so that
I know in some other experiments people have studied in not in your lab, but where the number of bosons per site could be like, I don't know, 100 or something, and then you have interesting correlations which are related to permanence, calculation of permanence and so on, which
definitely
thermalization and all. Anyway,
but here, since we're working with fairly small systems, we can actually do that. If we go for slightly larger systems, eventually one can probably also cap the Hilbert space at like 5 or 6 or so, but this was not even necessary here. So the Hilbert space for the 12-site system is about 1.3 million.
I see. Okay. Yeah. Thank you.
We definitely got time for more questions. And people also ask a lot of questions during the talk. So, okay, if not, let's thank Julian again.